Okay, so the goal of this video is going to be to do the finite element modeling of this problem over here, okay? All right, so let us first do the modeling of the root over here. I don't like much the quality, but I think it's a scanner. Okay, so 1.6, 0.8, okay? So maybe let's use millimeters. So it would be, okay, so let me put it maybe, all right, I think I got it, so I can close it. So let's do geometry points, those on top. So let's say we move to 400, 0, 0, okay. Then we have another one at 800. Negative 800. Now we move down to negative 400. We should have another one here at 800 and another one at 0.0. Okay, so you can see it over here. Now we need to move to the other end over here. So we know it's at 4 meters, so 4,000, and it's 0.4, 0.8. So we move here at 4,000 millimeters. And this would be, let's say, 200. Let's see if that is correct. So it would be, yeah, 200. Let's do, okay, we can do the 0 first. Now we can do minus 400. And the positive 400. All right. Now we move down to negative 1200. We do the negative 400. And we do 0.0. All right. So now if I put it sideways, that's what it looks like. Let's create the panel. So geometry, surface, corners, method on point. And let's start by the top ones. First panel. Now let's do the bottom ones. Okay. Side panels. And even though it's not on the problem, we're probably gonna need one here. Okay. All right, now let us model material new. Here, the units are not that important because we're not calculating deflections. So if I use aluminum 24, 75 to the 9, remember here, this is not 100% correct because we are using millimeters and this would be Newton meters. So, but it should not affect the result because we're not concerned about deflections. Now, we activate this by double clicking, properties, new. So we have a plate, which is 3 millimeters. We have a plate, which is 2 millimeters. And now we have the different rods. So basically what I'm doing is this. 2 millimeters, this one 3 millimeters, and the booms will be 900 and 1200. So we have booms, we're going to use rod elements. So let's see, one would be 900. So let's say rod 900 millimeters square. And another one will be rod 1200. And okay. All right, so we should have all the properties here on the left-hand side. So let's maybe start, if I do the mesh size, so mesh control, size along curve. So I want to do a mesh that we only consider quadratic elements, okay, for the plates. So let me choose for these ones here. And let's say for these ones, I want 40 elements. Okay. Now let's see for this one, this one, that one, that one. So I want 8 elements. So now this one, that one, that one, that one, that one, that one, that one. Let's say also want 8 elements. Okay. So now let's do the meshing, mesh geometry surface. So let's see, we mesh that one and that one. Okay. Should be with the plate 3. Okay. Oh. Okay, we didn't use 40 elements on top. Okay, so something wrong here. Control Z. I mean, this is not bad either, but this is not what we decided. So Control Z. So let's see. Let's do one by one. So mesh control, size along curve. Okay, I don't know what happened to this 40 here. Okay, mesh geometry surface. Okay, okay, so that's correct. Mesh geometry size along curve. So we selected these ones earlier, but looks like we didn't do it. Okay. Mesh geometry surface. This one with the 3 millimeters. All right. Okay. So I don't know if the top ones are going to work. Mesh geometry surface. Let's try one by one. It should be 2. You see, it's not working. So Control Z. All right. So mesh control, size along curve. 40. Okay. Mesh control, size along curve, and we say 8 and 8. Okay, that should be good. Mesh geometry surface. Okay. 2. Okay. Okay. Let me double click here so we know that one is active. All right, let's do the same thing for the other one. I don't know why we need to redo this. Down. So 40. And 8. So that one looked like it was good. All right. Same thing for the other one. Okay, you see this one were not defined. I don't know why. For this one, yes. Okay. So mesh geometry surface. One here. 2. Okay. Mesh control size along curve. Okay. All right, so I'm going to try. Hopefully, it would work directly in geometry surface. Okay. Okay, that's good. So now I'm going to mesh the tip over here. Mesh control size along curve. That should be. Okay, let's see what it does. No, I don't want to do. Sorry. Mesh control size along curve. So the whole curve, we want 16. Okay, and then on this one and this one, we should want 8. Okay, mesh geometry surface here, it should not matter with what you. Okay, let's go with the 3 or the 2. Okay, so does that look correct? Yeah. Now, mesh geometry curve. So that one, and the other one over here should be the 900 road. And now mesh geometry curve, and this curve and the lower curve over there should be with the 1200. Okay, let's use a little trick here to see if we really have all the elements. All right, looks like everything is there. And go to tools, check coincident nodes, select all. Okay, preview. That looks about right. Done. And okay. All right. Now let's clamp this end over here. So model, constraint on curve. Let's say here fix or clamp or cantilever, whatever you want. We select that curve. Okay, and we say fix. Okay, you should have letter X appearing. All right. Now we apply the load. Model, load, model. So this would be the 100 kilonewtons. Okay. So I select this one over here. Okay, force is 100 kilonewtons, but because we use millimeters, I'm just going to put 100, okay? And okay. Hopefully that would work. Or should I use 100? We'll figure it out. This part here. No, 100 might work. Okay. All right, so we have here our model. So file, save as. I should have a temp folder here. Let's say model 1, save, yes. Okay, so let's analyze this one. Create a set, new. Okay, analyze. All right, before we do anything, click F5 to see if the deformation looks correct. Oops, so we need to select cancel first, select the output. Oh, I did not select any output. I think I run it too fast then. Let's see, run. Last one, finish. Okay, I closed it too fast before. Enough time to save the results, so F5. Okay, so look at the formation for not just the total translation, and in contour, I mean, it doesn't matter, but total translation as well. Okay, contour, deform. Okay, all right, so that about the appropriate deformation. Okay, so in the problem, we were asked to do all this calculation at a cut 2 meters from the fixed end, so 2 meters along this length, okay? And there we needed to calculate the stresses and the shear flows. So for this model that we just did, we're just gonna check the actual stresses at 1, 2, 3, 4, 5, 6, the bending stresses. All right, so let's do the cut. You can come over here to remove the deformation. Click on F8, YZ. Okay, Control A. Now you can go to Tools, Work Plane. Here we are on the plane. You see here YZ. So draw work plane. Select the plane. So you need to remove the X over here and add the Z. So you added one over here. You can do a preview. Okay, so we're at 2 meters here, so 2000 millimeters. We're gonna create a group on the left-hand side, new, create this one, cut, let's say at 2 meters. Okay, you go on top to group, element ID. You have this feature showing up, this box showing up, pick box. You can come here and select around all these ones. Okay, and if you select a bunch of elements, you say, okay. Now you go here to groups, right click and say show active group. You will only show that elements on the cut. Tools, work plane, remove the draw work plane. All right, so let's see what would be the bending stresses at the boom. So let's do F5, deform. Okay, so I want to look at the road actual stress. Okay, so I think we should have multiplied by 1,000. Okay, so this is going to be correct, but maybe let's just rerun it. So if you want now, delete here the results. So right click and say delete. These are undo. On the load here, go to loads. Open here, loads on body. Right click, edit load. And here just put the kilonewtons, which we have done it earlier. Okay. You go to file, rebuild, yes. And you just click again the little gear on top to analyze. Okay, it will give us new results. Here they are. We can close this one. Click on results, and now we have these ones. Okay, showing here the boundary conditions and probably the other end the load. Let's see. No, okay. If you want to remove this F, I think just click over here. No, just click that one. Control A will center the image by itself. So here you can see, I mean, let's change this F5 instead of contour per material. And you see this would be what, about 52.5, 53, 59. This side has more because that's the side where the bending is applied. So this one is negative because in compression, and the bottom is positive because it's in tension. Let's see if I can magnify these values. F6, for here 12. Want to change the color, maybe you can change the color to, let's say, black. Okay, apply, let's see, that's better. That will look better. or not? 14. Yeah, that's better. Okay, so basically you see the one would be on the 50s. The reason why this one is higher is because the moment the force was on that side. So you come here, show full model. You see the force over here. So the final element will tell you that really the bending moments here is not the same for the three of them, which is what we did assume when we did the calculations. Okay, so let's see what we have in the calculation. We assume the moment at the cut was the same one. All right, 2000 kilonewtons. So mx was always the same one, but in real life, if you do detail, the moment here, here, and here will be slightly different. So in our calculation, we found that the stresses at 1, 2, 3 was about compression, nearly 55, and the same one over here at the bottom, but they were all the same, okay? Because we assume the moment to be constant. But as you can see over here, because this force is not applied right in the middle, is going to be vertical deformation, but the same some type of torsion, as you can see over here. So the moment on this side in the real life is not the same as this one. So the final element is able to capture those differences. Okay, so you see here the comparison actually is not bad between the finite element and the analytical solution. Okay, now in order to check the value of the shear, it's more complicated. So because we cannot really compare one-to-one, because here we use plates, but when we did the calculations over here, if you remember, in order to simplify the calculations, once we move here, all right, otherwise we needed to use this term over here, okay? But if we just assume that these were not active in carrying any shear, we assume this term to be 0, we simplify the equation to this one, so we did not have to do the integration, and that's how we find the shear flows. The main problem, I don't know if I mentioned it, okay, is that by doing this, what we're assuming is that the shear flows are constant. Well, let's say 1 and 2 over here, or let's say between 2 and 3, they are constant. But that's not the real case. In the real case, it will be kind of constant, then they will have like some type of semicircle, and then it will be constant again here, okay? And that's what the final element will show us. So I try to do, it will not be exact, but to show you how to do some type of validation between this and the final element on the next video. Okay? All right, so I'm going to terminate here this video. And oh, if you want here, maybe we can check something. Go to F5. Okay, so let's see, we do the stresses on the, so I don't know if we need to take the X. I mean, normally it would be the X, but I think for our notation here, the way the elements are oriented would be the Y. We need to try. This one should be about the same, and you see it's about correct. 60, 50s, 50 on top. I'm not sure why this one is 1 0. This one should be about 50. Let me try the other one. F5. Okay, now reverse. Okay, so what happened is that for some element, the orientation is different for this one than this one. So you see the ones that were 0 before gives about the right value now. And okay, so you see it's tricky. And that has to do because the way it was meshed, probably this one, the orientation was taking the X in that direction, the Y in that direction. You see this one will have the X in that direction, the Y in that direction. But this one will have actually the X in that direction and the Y in that direction. All right, so that's going to be cleaned up by doing some manipulation to orient all the elements on the same direction, but that will complicate a lot this modeling. Okay, so just go back to the other one on the booms, 5. So rod, function stress. Okay, and that one should be okay. All right, so let me terminate here the video. I'll stop the video and